Imagine floating peacefully in the darkness between galaxies, gazing upon our cosmic home from impossible distances. Before you stretches the Milky Way, a magnificent spiral of 400 billion stars, its graceful arms sweeping across 100,000 light-years of space in elegant curves of starlight and cosmic dust. This is the galaxy that cradles our solar system, the vast stellar community that has nurtured our sun for over 4.5 billion years. But this breathtaking spiral structure we call home began its journey as something entirely different, a chaotic collection of smaller stellar communities scattered across the cosmic void, showing no hint of the elegant architecture it would one day achieve. The story of how our galaxy transformed itself from cosmic chaos into this spiral sanctuary is one of the most remarkable tales in the universe, a gentle epic spanning 13 billion years of patient cosmic evolution. To understand this extraordinary transformation, we must first return to where we left our cosmic story in our previous journey together. We had witnessed the universe's first billion years, from the Big Bang's elegant simplicity through the formation of the very first stars that ended the cosmic dark ages. We explored how those ancient stellar pioneers, the massive population 3 giants, lived brief but crucial lives before dying in spectacular supernova, scattering precious heavy elements like carbon, oxygen, and silicon throughout space for the first time in cosmic history. We concluded that first journey by observing the remarkable fertility of the universe during those early epochs, its extraordinary capacity to generate complexity from simplicity and beauty from chaos. The first galaxies had begun to form as chaotic assemblages of young stars, marking the beginning of truly complex astrophysical systems that would reshape the cosmos forever. The extraordinary fertility of the universe during those early epochs cannot be overstated. As the cosmic dark ages drew to their close, the seeds of countless galaxies were taking root in the invisible scaffolding of dark matter that permeated all of space. Like flowers blooming in a vast cosmic garden, these early stellar nurseries began to illuminate the darkness with their gentle newborn light. The universe was transitioning from a realm of simple hydrogen and helium into something far more complex, a tapestry of elements that would eventually give rise to planets, life, and consciousness itself. Among these countless galaxies that emerged from the cosmic dark ages, one particular gathering of stars and gas began a journey that would eventually become our home. This was not yet the majestic spiral we know today, but rather a collection of smaller stellar communities, drawn together by gravity's patient hand across the vast expanses of space and time. In those early moments of galactic formation, roughly 13 billion years ago, the ingredients of what would become the Milky Way were scattered across a region of space hundreds of thousands of light-years wide. The story we are about to unfold is one of transformation, a gentle epic spanning billions of years, during which countless stellar generations lived and died, each contributing their essence to the growing complexity of our galactic home. It is a tale of recycling on the grandest possible scale, where the deaths of stars become the birthplaces of new worlds, and where the very atoms in our bodies carry the memory of stellar furnaces that burned billions of years before our sun was even a whisper of possibility. As we settle into this contemplative journey through time, imagine floating peacefully above our galaxy, watching its story unfold across the eons like pages turning in the universe's most magnificent book. The Milky Way we see today, that graceful spiral of stars, gas, and dust stretching across our night sky, is the culmination of one of the longest and most beautiful stories ever told. It is a story written in starlight and cosmic dust, in the gentle dance of gravity and the patient alchemy of stellar evolution. Our galaxy's journey begins in an era when the universe itself was still in its cosmic childhood, barely a billion years old. The cosmos was a simpler place then, filled primarily with hydrogen and helium, the lightest elements forged in the Big Bang's first few minutes. There were no rocky planets yet, no carbon-based molecules, no complex chemistry that could give rise to life as we know it. Yet even in this apparent simplicity, the seeds of extraordinary complexity were being sown. The Milky Way's story is fundamentally one of growth and enrichment. Like a river gathering tributaries as it flows toward the sea, our galaxy has grown through the gentle accumulation of smaller stellar communities, each bringing its own unique contribution to the whole. Over the course of 13 billion years, it has evolved from a collection of ancient, metal-poor stars into the rich, layered structure we inhabit today, a galaxy with over 400 billion stars, countless planets, and the complex chemistry necessary for life itself. This transformation did not happen suddenly or dramatically. Instead, it unfolded with the patience that characterizes all cosmic processes, each change building gently upon what came before. Stars were born, lived their lives, and died, returning their enriched material to the galactic medium, where it could be incorporated into new generations of stars and planets. This cosmic recycling program has been running continuously for billions of years, gradually transforming the simple hydrogen and helium of the early universe into the 92 naturally occurring elements that make up the periodic table. Throughout this long journey, our galaxy has been shaped by forces both gentle and dramatic. Gravity has been the primary architect, patiently sculpting the grand spiral structure we see today. But there have also been moments of more dramatic change, collisions with smaller galaxies, the formation of stellar nurseries, the spectacular deaths of massive stars. Each of these events has left its mark on the galactic structure, like layers in an ancient tree recording the passage of seasons. The Milky Way's evolution can be understood as a series of great chapters, each representing hundreds of millions or billions of years of development. In the earliest chapter, we witness the birth of our galaxy from the merger of smaller proto-galaxies, a gentle collision that began the process of galactic formation. The second great chapter tells the story of how these early building blocks organized themselves into the galaxy's fundamental architecture, the central bulge, the thick disk, and the beginnings of spiral structure. The third chapter is perhaps the most crucial for our own existence, the great galactic recycling program that gradually enriched the galaxy's gas with heavy elements. This was the era when carbon, oxygen, silicon, and iron, the building blocks of rocky planets and life itself, were forged in stellar cores and distributed throughout the galaxy by dying stars. Without this patient process of stellar alchemy, neither our sun nor our Earth could have formed. The fourth chapter describes the formation of the thin disk where we now reside, a more recent addition to the galaxy's structure that contains most of the stars we see in our night sky. This is where our own solar system would eventually form, in a quiet region far from the galactic center, where conditions were just right for the emergence of planetary systems capable of supporting life. The final chapter brings us to the present day, where we find ourselves as conscious observers, able to contemplate our galaxy's long history and peer into its future. We are living participants in this ongoing story, made of atoms forged in ancient stars, inhabitants of a planet orbited by a star, that is itself part of the galaxy's continuing evolution. As we embark on this journey together, we'll discover that the Milky Way is not just our cosmic address, it is the repository of our deepest origins. Every carbon atom in our bodies, every calcium atom in our bones, every iron atom in our blood was forged in the nuclear furnaces of stars that lived and died long before our sun was born. We are quite literally made of star stuff, and our galaxy is the crucible in which that star stuff was refined over billions of years into the complex chemistry that makes life possible. The story we're about to explore unfolds across scales both vast and intimate. We'll witness events that shaped hundreds of billions of stars while also discovering how these grand cosmic processes ultimately led to the formation of our own small corner of the galaxy. We'll see how the deaths of massive stars billions of years ago created the very elements that flow through our veins today, and how the patient dance of gravity and time created the stable galactic environment in which our solar system could form and life could flourish. This is a story best told slowly, with the patience that the universe itself has shown in crafting our cosmic home. As we journey through these 13 billion years together, we'll pause often to contemplate the deeper meanings hidden in each chapter of galactic evolution. What does it mean that we are made of ancient starlight? How should we understand our place in a story that spans such vast reaches of time and space? These are questions that invite not quick answers, but gentle reflection, the kind of deep contemplation that comes naturally when we truly grasp the magnificent scope of our cosmic heritage. In the cosmic dawn, when the universe was barely 2 billion years old, the region of space that would eventually become our Milky Way was a very different place than it is today. Instead of the graceful spiral we know, there existed a loose collection of what astronomers call proto-galaxies, smaller assemblages of stars and gas, each containing perhaps a few million to a few billion stars, scattered across a volume of space, hundreds of thousands of light years in extent. These proto-galaxies were the children of the universe's first great phase of star formation, born in the dense regions where dark matter had begun to coalesce in the cosmic web. They were ancient even by galactic standards, composed primarily of stars that had formed from the nearly pure hydrogen and helium left over from the Big Bang. These population 3 stars, as astronomers call them, were unlike anything we see in our galaxy today, massive, brilliant, and short-lived, containing virtually no elements heavier than helium. The birth of our galaxy began not with a single moment of creation, but with a gentle gravitational ballet that played out over hundreds of millions of years. Like dancers slowly drawn together by an irresistible cosmic choreography, these proto-galaxies began to spiral inward toward their common center of mass. The process was governed by the patient mathematics of gravity, each stellar system following the curved paths through space-time that Einstein's equations describe. As these early galactic building blocks drew closer together, their interactions became more complex and beautiful. Some passed close enough to exchange stars and gas, like celestial ambassadors sharing gifts between their respective communities. Others merged completely, their stellar populations mixing like streams, converging into a river. Throughout this process, the combined gravitational field of the growing system began to trap and heat the vast clouds of gas that filled the spaces between the stars. The merger process was surprisingly gentle, despite the vast energies involved. When 2 proto-galaxies collided, their stars rarely collided with each other. The distances between stars are so vast that they could pass through each other's stellar systems like phantoms. Instead, the gravitational interactions would scatter some stars into new orbits while drawing others closer to the growing galactic center. The real action happened in the gas clouds, which did collide, creating shock waves that compressed the material and triggered new episodes of star formation. During these early merger events, something remarkable was happening to the chemical composition of the galaxy. The massive population 3 stars that had dominated the first stellar generation were reaching the ends of their brief but brilliant lives. When such massive stars die, they do so in spectacular fashion, as supernovae that outshine entire galaxies for weeks or months. These cosmic explosions served as the galaxy's first chemical factories, forging elements like carbon, oxygen, magnesium, and silicon in their nuclear furnaces, and then dispersing these precious materials throughout the surrounding space. With each supernova explosion, the interstellar medium became slightly more enriched with these heavier elements, what astronomers call metals, even though they include many elements that chemists would classify differently. This gradual chemical enrichment was crucial for the galaxy's future development. Stars that formed from this enriched gas would have fundamentally different properties than their predecessors. They could be smaller and longer-lived, and the planets that formed around them could be rocky worlds rather than just gas giants. The process of galactic assembly was also shaped by the invisible architecture of dark matter. While we cannot see dark matter directly, its gravitational influence was crucial in determining the ultimate structure of our forming galaxy. The dark matter formed a vast, roughly spherical halo that extended far beyond the visible stars, providing the gravitational framework within which normal matter could organize itself. This dark matter halo acted like a cosmic scaffolding, its gravitational wells guiding the infall of gas and the orbital patterns of the emerging stellar populations. As the merger process continued, the growing galaxy began to develop its first architectural features. The central regions, where the gravitational field was strongest, became increasingly chapelly dense with stars. This was the beginning of what we now call the galactic bulge, a roughly spherical concentration of ancient stars that surrounds the galaxy's central black hole. The stars in this bulge carry the memory of the galaxy's violent youth in their orbital patterns, which remain highly elliptical and randomly oriented, like fossils of the chaotic merger process that created them. During this epoch of galactic formation, temperatures in the galaxy's central regions were extraordinarily high. The gravitational energy released by the ongoing mergers heated the gas to millions of degrees, creating a hot, turbulent environment that glowed brightly in X-ray wavelengths. This hot gas phase would have been visible across cosmic distances, marking our forming galaxy as an active participant in the universe's early era of rapid galactic assembly. The timescale of these processes is almost impossible to comprehend from our human perspective. The merger events that created our galaxy's foundation unfolded over periods longer than complex life has existed on Earth. Yet from the cosmic perspective, this was a relatively rapid phase of galactic evolution. Within about 1 billion years, from roughly 12.5 to 11.5 billion years ago, the fundamental structure of our galaxy's central regions had been established. By the end of this formative period, our proto-Milky Way had grown to contain perhaps 50 to 100 billion stars, organized into a central bulge, surrounded by a more extended stellar halo. The galaxy's first supermassive black hole had formed at its center, fed by the enormous quantities of gas and dust that were flowing inward as a result of the merger process. This black hole, which today has a mass equivalent to about 4 million suns, was already beginning to influence the galaxy's evolution through its powerful gravitational field and the energetic jets it produced when actively feeding. The stellar population that emerged from this epoch was fundamentally different from what we see in our galactic neighborhood today. These ancient stars, which we can still observe at the galaxy's halo and bulge, are metal poor by modern standards, containing perhaps 1/100th the concentration of heavy elements found in our sun. Their reddish colors and relatively low masses reflect the chemical simplicity of the era in which they formed, when the galaxy's chemical enrichment program was still in its infancy. Yet even these ancient stars represent a crucial step forward in cosmic chemical evolution. Unlike the very first generation of stars, which contained virtually no heavy elements, these second-generation stars were able to form planets, though those planets would have been very different from Earth, without sufficient quantities of silicon, magnesium, and iron. These early planetary systems would have consisted primarily of gas giants and perhaps water-rich worlds, lacking the rocky terrestrial planets that seem necessary for the kind of complex chemistry that gives rise to life. As this first great chapter of galactic evolution drew to a close, our young Milky Way was still far from the structured spiral we know today. It was more like a cosmic construction site, a dynamic, evolving system where new stars were being born at a prodigious rate from the gas and dust left over from the merger process. The stage was set for the next phase of galactic evolution, during which this loose collection of stars and gas would organize itself into the more familiar structures we observe in galaxies throughout the universe today. The birth of our galaxy was not a single event but a process, a gentle gathering of cosmic materials that played out over vast stretches of time and space. In this patient assembly, we can see the universe's fundamental tendency toward increasing organization and complexity. From the simple hydrogen and helium of the cosmic dawn, gravity and nuclear fusion were beginning to weave the rich tapestry of elements and structures that would eventually give rise to planets, life, and consciousness itself. As the great merger epoch drew to its close, our young galaxy found itself at a cosmic crossroads. The violent, chaotic phase of initial assembly was ending, but the story of the Milky Way was far from complete. The foundation had been laid, a central concentration of ancient stars surrounded by a more extended halo, all held together by gravity's patient embrace. But this loose confederation of stellar systems was about to undergo a remarkable transformation, organizing itself into the elegant structures that characterize spiral galaxies throughout the universe. The transition from this early chaotic phase to the next chapter of galactic evolution was marked by a subtle but profound change in the galaxy's behavior. The rate of major mergers began to slow as the galaxy incorporated most of the smaller proto-galaxies in its immediate vicinity. This allowed the gravitational field to stabilize and the remaining gas to settle into more organized patterns of motion. Like a cosmic symphony transitioning from a turbulent opening movement to a more structured theme, our galaxy was preparing to reveal its architectural possibilities. In the era following the Great Merger epoch, roughly 8 to 10 billion years ago, our galaxy entered what we might call its architectural phase, a period during which the loose collection of stars and gas left over from the early mergers began to organize itself into the fundamental structures that characterize spiral galaxies. This was the era when the Milky Way developed its thick disk established its basic spiral pattern, and began to exhibit the kind of organized rotation that we observe in mature galactic systems today. The transformation began with the vast quantities of gas that remained in the galaxy after the merger phase. This gas, heated to high temperatures by the violence of galactic assembly, slowly began to cool and settle inward under the influence of gravity. As it did so, conservation of angular momentum, the cosmic equivalent of a figure skater pulling in her arms to spin faster, caused the gas to flatten into an increasingly thin, rotating disk. This process of disk formation was both beautiful and complex, involving physics that operates on scales from individual atoms to entire stellar systems. As the hot gas radiated away its thermal energy into space, it lost the random kinetic energy that had supported it against gravitational collapse. Gravity then drew the cooling gas inward, but because the entire system was rotating, the infalling material couldn't simply fall straight into the galactic center. Instead, it settled into circular orbits, forming an extended disk structure that grew thicker and more massive over time. The formation of the galactic disk was not a smooth, uniform process. Local variations in gas density created instabilities that grew over time, eventually organizing themselves into the spiral structure that is one of the most striking features of our galaxy today. These spiral arms are not permanent features. They are actually pressure waves that propagate through the galactic disk like ripples on a pond, compressing the gas and triggering new episodes of star formation as they pass. During this architectural phase, our galaxy was experiencing one of the most prolific periods of star formation in its history. The settling gas provided an abundant supply of raw material for stellar nurseries, while the spiral density waves created the compression needed to trigger gravitational collapse in molecular clouds. The result was a burst of stellar activity that populated the galaxy's thick disk with a generation of stars that we can still observe today. Stars that are intermediate in age between the ancient halo population and the younger stars of the thin disk. The thick disk stars that formed during this epoch have a different character than either their predecessors or their successors. They are more metal-rich than the halo stars, reflecting the continued chemical enrichment of the galaxy's gas supply, but not as metal-rich as the stars that would form later. Their orbital patterns also tell a story of the galaxy's evolution. They move in slightly elliptical orbits that carry them well above and below the galactic plane, a reflection of the still somewhat chaotic conditions that existed when they formed. One of the most remarkable aspects of this architectural phase was the emergence of the galaxy's spiral structure. The physics behind spiral arm formation is surprisingly subtle, involving what astronomers call density wave theory. According to this model, the spiral pattern represents a long-lived pressure wave that rotates through the galactic disk more slowly than the stars themselves. As stars orbit the galaxy, they periodically pass through these spiral arms, where the increased density triggers enhanced star formation and creates the bright blue appearance that makes the spiral pattern visible. The spiral structure serves as more than just a beautiful ornament on our galaxy. It plays a crucial role in regulating star formation and mixing the galactic gas. As molecular clouds encounter the spiral shock fronts, they are compressed and fragmented, triggering the collapse that leads to new star formation. The massive, short-lived stars that form in these regions quickly enrich the surrounding gas with heavy elements through stellar winds and supernova explosions, gradually increasing the metallicity of the galactic disk. During this architectural phase, our galaxy also began to develop some of the features that make it particularly hospitable to life. The spiral structure helped to regulate star formation, preventing the galaxy from converting all its gas into stars too quickly, while ensuring a steady supply of heavy elements. The rotating disk provided a stable, dynamical environment where stellar systems could maintain regular orbits over billions of years, and the gradual chemical enrichment of the disk was creating the conditions necessary for the formation of rocky, terrestrial planets. The central regions of the galaxy were also evolving during this period, though more quietly than during the merger epoch. The supermassive black hole at the galactic center had settled into a more regular feeding pattern, consuming gas and dust that spiraled inward from the disk. While still active, it was no longer the violent, quasar-like object it might have been during the early merger phase. Instead, it had become what astronomers call a low-luminosity, active galactic nucleus, powerful enough to influence the galaxy's evolution, but not so violent as to disrupt the star formation taking place in the disk. The thick disk that formed during this epoch represents about 10 to 15% of the stars in our galaxy today, and these stars carry important information about this crucial phase of galactic evolution. They tend to be older than the Sun, with ages ranging from about 8 to 12 billion years, and they show a wide range of chemical compositions that reflect the ongoing enrichment of the galactic medium. Some of the thick disk stars are quite metal poor, formed early in this epoch when the galaxy's chemical evolution was still in progress, while others approach the metallicity of the Sun. One of the most intriguing aspects of thick disk formation is that it appears to have been a relatively brief phase in galactic evolution. Most thick disk stars formed within a period of just a few billion years, after which star formation in this component largely ceased. This suggests that some significant change occurred in the galaxy's structure or gas supply that redirected subsequent star formation into the thinner disk structure that we observe today. The end of the thick disk formation epoch was marked by a gradual but profound change in the galaxy's star formation patterns. The initial burst of activity that had populated the thick disk began to subside as the most easily accessible gas was consumed, and the galaxy settled into a more mature configuration. The spiral structure, which had been somewhat irregular and chaotic during the early phases of disk formation, began to stabilize into the more regular pattern we observe today. This transition also coincided with changes in the galaxy's chemical evolution. The massive stars that had driven the early phases of heavy element production were beginning to give way to a more diverse stellar population that included smaller, longer-lived stars. This shift had important implications for the galaxy's future evolution, as it meant that chemical enrichment would continue at a steadier, more gradual pace, rather than in the dramatic bursts associated with clusters of massive stars. By the end of this architectural phase, roughly 8 billion years ago, the Milky Way had developed most of the structural features that characterize it today. It had a central bulge populated with ancient metal-poor stars, a thick disk containing intermediate-age stars with moderate metallicity, and a well-established spiral pattern that regulated ongoing star formation. The stage was now set for the next great chapter in galactic evolution, the long, slow process of chemical enrichment that would eventually create the conditions necessary for the formation of our solar system and the emergence of life itself. The architectural phase of galactic evolution represents a crucial transition in our cosmic story. During this epoch, the Milky Way transformed from a chaotic collection of stellar systems into an organized spiral galaxy capable of supporting the long-term processes that would eventually give rise to planetary systems like our own. It was during this time that the galaxy developed the stable, rotating disk structure that has persevered for billions of years, providing the gravitational and chemical environment necessary for the slow alchemy of stellar evolution to work its transformative magic on the raw materials of the cosmos. As we pause in our journey through cosmic time, consider the remarkable patience exhibited by our galaxy during this architectural phase. Over the course of billions of years, gravity slowly but persistently organized the chaotic remnants of the merger epoch into the elegant spiral structure we know today. This process required no conscious design, no deliberate intention, only the persistent application of physical laws operating across vast scales of space and time. What does this tell us about the nature of complexity in the universe? How does it change our perspective to know that the beautiful spiral pattern of our galaxy emerged not through sudden creation, but through billions of years of gradual self-organization? In the galaxy's patient architecture, we can perhaps see a reflection of all the slow processes that have shaped our world. The gradual evolution of life, the patient accumulation of knowledge, the slow but persistent changes that occur in our own lives when we allow time to work its transformative magic. As the Milky Way settled into its mature spiral structure, the stage was set for one of the most crucial processes in cosmic evolution, the Great Galactic Recycling Program that would gradually transform the simple hydrogen and helium of the early universe into the 92 naturally occurring elements of the periodic table. This process, driven by the life cycles of stars, would unfold over billions of years, slowly but steadily enriching the galaxy's gas supply with the heavy elements necessary for rocky planet formation and, ultimately, life itself. The architectural phase had provided the framework within which this chemical evolution could proceed. The stable disk structure ensured that newly created elements would be efficiently mixed throughout the galactic medium, while the spiral arms provided the compression needed to trigger ongoing star formation from increasingly enriched gas. As we transition into this next chapter of our story, we move from the realm of galactic mechanics into the more intimate world of stellar alchemy, where the fundamental building blocks of planets and life are slowly forged in the nuclear furnaces of countless generations of stars. In the middle chapters of our galaxy's story, roughly 6 to 8 billion years ago, the Milky Way embarked upon its most crucial transformation, a vast, patient recycling program that would gradually convert the simple hydrogen and helium of the cosmic dawn into the rich array of elements that make planets and life possible. This chapter of galactic evolution is written not in the dramatic language of collisions and explosions, but in the quieter poetry of stellar life cycles, each star a small but essential participant in the galaxy's grand chemical evolution. The Great Galactic Recycling Program operates on a principle both simple and profound. Stars are cosmic alchemists, transforming lighter elements into heavier ones through the nuclear fusion processes that power their luminous lives. When these stellar furnaces reach the end of their lives, they return their enriched material to the galactic medium, where it can be incorporated into new generations of stars and planets. Over billions of years, this process gradually increases the complexity and diversity of matter in the galaxy, creating the chemical foundation for rocky worlds and organic chemistry. During this epoch, the Milky Way was populated by three distinct stellar populations, each contributing to the chemical enrichment process in its own way. The ancient halo stars, relics of the galaxy's violent youth, continued their lonely orbits in the galactic suburbs, slowly burning their meager supplies of hydrogen and contributing little to ongoing chemical evolution. The thick disk stars, products of the earlier architectural phase, were entering their mature years, with the most massive among them beginning to reach the ends of their lives and return their moderately enriched material to space. But it was the emergence of a new stellar population that truly characterized this epoch, the first stars of what would become the galaxy's thin disk. These stars formed from gas that had been progressively enriched by previous generations of stellar evolution, and they represented a qualitative leap forward in cosmic chemistry. Unlike their predecessors, these stars formed from material that contained significant quantities of elements like carbon, oxygen, nitrogen, and silicon, the building blocks of rocky planets and organic molecules. The process of stellar nucleosynthesis that drives this chemical evolution is one of nature's most elegant engines of transformation. In the cores of stars, where temperatures reach tens of millions of degrees and pressures are billions of times greater than anything on Earth's surface, hydrogen nuclei are forced together with such violence that they overcome their natural electrical repulsion and fuse into helium. This process, which powers the sun and every other star, releases the energy that makes stars shine while slowly converting hydrogen into more complex elements. Moin Meksho in Presco. For stars like our sun, this nuclear alchemy proceeds through a well-understood sequence of fusion reactions. Hydrogen fuses into helium in the stellar core, releasing energy that supports the star against gravitational collapse. As the hydrogen fuel in the core is gradually exhausted, the star's central regions contract and heat up, eventually becoming hot enough to fuse helium into carbon and oxygen. This process continues up the periodic table, with each successive fusion stage requiring higher temperatures and producing heavier elements. The most massive stars, those with masses 8 times greater than our sun, carry this nucleosynthesis chain all the way to iron, the most stable nucleus in the periodic table. In their final moments, these stellar giants undergo core collapse and explode as supernovae, not only dispersing their newly forged elements throughout space, but also creating, in the extreme conditions of the explosion itself, many of the elements heavier than iron, gold, silver, platinum, uranium. All of these rare and precious materials are forged in the violent seconds of stellar death and scattered into the galactic medium to enrich future generations of stars and planets. The lower mass stars contribute to galactic chemical evolution through a gentler but no less important process. As they age and exhaust their nuclear fuel, these stars expand into red giants, developing powerful stellar winds that gradually strip away their outer layers and disperse processed material into space. When they finally shed their outer envelopes to become white dwarf stars, they leave behind beautiful planetary nebulae, glowing clouds of gas that represent the star's final gift to the galaxy's ongoing chemical evolution. During this epoch of intense stellar recycling, the Milky Way's chemical composition was changing at an unprecedented rate. Each supernova explosion enriched thousands of cubic light-years of space with newly forged elements, while the gentler winds of dying red giants provided a steady supply of carbon, nitrogen, and other elements essential for organic chemistry. The spiral arms served as cosmic mixing bowls, stirring the enriched gas and ensuring that heavy elements were distributed throughout the galactic disk. The effects of this chemical enrichment were profound and far-reaching. As the metallicity of the galactic gas increased, the properties of newly forming stars began to change in subtle but important ways. Higher metallicity gas could cool more efficiently, allowing smaller, longer-lived stars to form. The presence of dust grains, which form when heavy elements condense in the cool outer layers of stellar atmospheres, began to affect the star formation process itself, providing both cooling mechanisms and the seeds around which planets could eventually form. Perhaps most importantly, the increasing abundance of heavy elements made possible the formation of terrestrial planets, rocky worlds like Earth that could provide stable, chemically diverse environments suitable for the emergence of life. The silicon, magnesium, iron, and other heavy elements created in stellar cores and dispersed by supernovae slowly accumulated in the galaxy's gas supply, reaching concentrations that would eventually allow the formation of planetary systems capable of supporting complex chemistry and biology. This process of chemical enrichment was not uniform throughout the galaxy. The central regions where star formation had been most intense during the early epochs became enriched more rapidly than the outer regions. This created a metallicity gradient that we can still observe today. Stars in the galactic center are generally more metal-rich than stars in the galactic suburbs. Our Sun, located about halfway out from the galactic center, formed from gas with a metallicity that represents billions of years of patient stellar alchemy. The temporal pattern of chemical enrichment also tells an important story about galactic evolution. The earliest phases of enrichment, dominated by massive stars and supernovae, produced large quantities of oxygen, silicon, and iron, the elements that make up the rocky cores of terrestrial planets. Later phases, as lower mass stars began to contribute more significantly, added carbon, nitrogen, and other elements important for organic chemistry. This sequence of enrichment helped create the chemical conditions necessary for life as we know it. During this epoch, our galaxy was also experiencing important changes in its star formation patterns. The initial burst of activity that had characterized the thick disk formation was giving way to a more sustainable rate of stellar birth. The galaxy was learning to regulate its star formation, maintaining a steady but not excessive rate that would allow chemical enrichment to continue over billions of years without exhausting the gas supply too quickly. The spiral structure played a crucial role in this regulation. As gas clouds encountered the spiral shock fronts, they were compressed and triggered to form stars. But the efficiency of this process was carefully balanced. Too much compression would lead to a starburst that would quickly consume all available gas. Too little would result in insufficient star formation to maintain chemical enrichment. The galaxy found a middle path that allowed steady progress in chemical evolution while preserving enough gas to fuel star formation for billions of years into the future. By the end of this great recycling epoch, roughly 6 billion years ago, the Milky Way had achieved a level of chemical sophistication that made it capable of forming planetary systems like our own. The abundance of heavy elements in the galactic gas had increased by more than an order of magnitude since the galaxy's formation, reaching levels sufficient to support the formation of rocky planets, complex atmospheric chemistry, and the organic molecules that serve as the building blocks of life. The stellar populations that emerged during this epoch carry the chemical signature of this remarkable transformation. Unlike the metal-poor stars of the halo and thick disk, the thin disk stars that began forming during this period show abundances of heavy elements approaching or even exceeding that of our Sun. These stars represent the first generation of stellar systems in our galaxy that were truly capable of forming Earth-like planets, worlds with solid surfaces, diverse mineralogy, and the chemical complexity necessary for geological and biological processes. The Great Galactic Recycling Program represents one of the most important chapters in our cosmic story because it created the conditions necessary for our own existence. Every carbon atom in our bodies, every oxygen molecule we breathe, every calcium atom in our bones was forged in the nuclear furnace of a star that lived and died billions of years before our Sun was born. We are quite literally made of recycled star stuff, the end product of billions of years of stellar alchemy that gradually transformed the simple elements of the cosmic dawn into the complex chemistry of life. As this epoch drew to a close, the Milky Way stood poised to enter the final phase of its evolution, the formation of the thin disk structure in which our own solar system would eventually form. The chemical enrichment program had done its work, creating a galaxy capable of forming not just stars and planets, but worlds complex enough to support the emergence of life and eventually consciousness itself. The stage was set for the next chapter of our cosmic story, in which the grand processes of galactic evolution would finally create the conditions necessary for our own small corner of the universe to come into being. In contemplating this vast recycling program, we encounter one of the most profound truths about our cosmic heritage. The elements that make up our bodies, our planet, and everything we know have been cycling through the galaxy for billions of years. The calcium in our bones may have been forged in a massive star that exploded 8 billion years ago. The iron in our blood may have originated in a different stellar explosion in a distant part of the galaxy before slowly making its way to the molecular cloud that would eventually give birth to our solar system. This perspective transforms our understanding of both time and identity. We are not separate from the cosmos, but are active participants in its ongoing evolution. Our very existence represents the temporary organization of atoms that have been wandering the galaxy since long before Earth existed, and which will continue their cosmic journey long after we are gone. In recognizing this deep connection to the galactic recycling program, we perhaps find a new kind of humility and wonder at our place in the cosmic story. As the great epic of chemical enrichment drew toward its close, the Milky Way had become a fundamentally different place than the metal-poor galaxy of earlier eras. The patient alchemy of countless stellar generations had created a cosmos rich in the heavy elements necessary for rocky planet formation and complex chemistry. Now, approximately 6 billion years ago, the galaxy was ready to enter its most recent major phase of evolution, the formation of the thin disk structure that would become our immediate cosmic neighborhood and, eventually, the birthplace of our own solar system. This transition marked not just a change in the galaxy's structure, but a maturation of the entire galactic ecosystem. The wild, chaotic star formation of earlier epochs was giving way to a more measured, sustainable pattern of stellar birth that would characterize the galaxy's behavior for the remainder of its evolution. The spiral arms had stabilized into the elegant pattern we observe today, and the chemical composition of the galactic gas had reached the threshold necessary for forming planetary systems capable of supporting life. In the later chapters of our galaxy's story, roughly 3 to 5 billion years ago, the Milky Way entered what we might call its mature phase, a period during which the thin disk structure that contains our solar system began to take shape. This was the epoch when our galaxy developed its modern appearance and established the stable, chemically rich environment that would eventually give rise to planetary systems capable of supporting life. It was during this time that the quiet region of space where our sun would eventually form began to accumulate the enriched gas and dust necessary for the creation of rocky planets like Earth. The formation of the thin disk represents the final major architectural development in our galaxy's evolution. Unlike the thick disk that formed during the earlier epochs of violent star formation, the thin disk emerged gradually through a more gentle process of gas accretion and star formation. The galaxy had learned, in a sense, to regulate its stellar birth rate, maintaining a steady but sustainable level of activity that would allow it to continue forming stars for billions of years into the future. This thin disk structure, where most of the stars we see in our night sky reside, is remarkably flat, only about 1,000 light-years thick compared to the galaxy's 100,000 light-year diameter. This extreme flatness reflects the highly organized rotational motion that characterizes the mature galaxy. The gas from which thin disk stars form has had billions of years to settle into nearly circular orbits, creating a stellar population with much more regular orbital patterns than the elliptical, chaotic orbits of the thick disk and halo stars. The stars that formed during this epoch of thin disk development were fundamentally different from their predecessors. They formed from gas that had been enriched by billions of years of stellar recycling, with metallicities approaching or even exceeding that of our Sun. This chemical richness made possible, for the first time in galactic history, the formation of planetary systems truly similar to our own, systems with rocky inner planets, complex atmospheric chemistry, and the potential for liquid water on their surfaces. The location where our solar system would eventually form, about 26,000 light-years from the galactic center in what astronomers call the galactic habitable zone, was particularly favorable for the development of life-supporting planetary systems. This region of the galaxy struck an optimal balance between chemical enrichment and environmental stability. It was far enough from the galactic center to avoid the disruptive effects of frequent supernova explosions and the intense radiation environment near the central black hole, yet close enough to benefit from billions of years of chemical enrichment by previous generations of stars. During this epoch, the spiral structure of our galaxy was also playing a crucial role in regulating star formation and mixing chemical elements throughout the disk. The spiral arms acted as cosmic conveyor belts, shepherding gas clouds through regions of compression where they could collapse to form new stars, while also ensuring that the heavy elements produced by stellar nucleosynthesis were efficiently distributed throughout the galactic medium. This process created a remarkably uniform chemical environment within the thin disk, with metallicity variations of only a few percent across vast regions of space. The star formation process during this period was characterized by the emergence of what astronomers call stellar nurseries, vast molecular clouds where hundreds or thousands of stars could form together in loose associations. These star-forming regions, like the Orion Nebula we can see in our night sky today, were the cosmic maternity wards where most of the stars in our galactic neighborhood were born. The process was surprisingly efficient, converting about 1% of the mass of a molecular cloud into stars before stellar winds and radiation from the newly formed massive stars dispersed the remaining gas. One of the most remarkable aspects of thin disk star formation was the emergence of planetary systems as a common outcome of the stellar birth process. The dust grains that formed when heavy elements condensed in stellar atmospheres provided the seeds around which planets could grow. In the protoplanetary disks that surrounded newly formed stars, these dust grains slowly accumulated through gentle collisions, growing from microscopic specks into pebbles, then boulders, and eventually into the rocky cores of terrestrial planets. The chemistry of planet formation during this epoch was far richer and more complex than anything possible in earlier phases of galactic evolution. The abundant silicon, magnesium, and iron allowed the formation of rocky planets with solid surfaces and complex mineralogy. The presence of water, carbon dioxide, and other volatile compounds made possible the development of atmospheres and potentially oceans. The organic molecules that could form from carbon, hydrogen, oxygen, and nitrogen provided the chemical foundation for life as we know it. Our own solar system's formation story begins during this epoch, though it would not actually form until somewhat later, about 4.6 billion years ago. The molecular cloud that would eventually give birth to our sun and planets was gradually accumulating the enriched material dispersed by earlier generations of stars. Supernova explosions in our galactic neighborhood were adding their quota of heavy elements to this slowly growing reservoir of planet-forming material, while the deaths of lower-mass stars contributed carbon, nitrogen, and other elements essential for organic chemistry. The galactic environment during this period was remarkably stable compared to earlier epochs. The rate of supernova explosions had decreased significantly as the most massive stars from earlier generations had already completed their brief lives. This reduced the level of high-energy radiation and cosmic rays that could disrupt planetary atmospheres and interfere with the development of life. The galaxy had entered what we might call its Goldilocks epoch, not too violent to prevent the development of stable planetary systems, not too quiet to cease the chemical enrichment necessary for continued evolution. The formation of the thin disk also marked the establishment of the Milky Way's modern rotation curve, the relationship between orbital velocity and distance from the galactic center that reflects the distribution of both visible matter and dark matter throughout the galaxy. This rotation curve has remained remarkably stable over the past several billion years, providing the kind of long-term gravitational environment necessary for planetary systems to maintain stable orbits over geological timescales. During this epoch, our galaxy was also beginning to interact more significantly with its satellite galaxies, particularly the large and small Magellanic Clouds. These gravitational interactions, while gentle compared to the major mergers of earlier epochs, began to trigger additional episodes of star formation in the outer regions of the galactic disk and to distort the galaxy's structure in subtle ways that we can still observe today. The chemical evolution of the galaxy during this period was characterized by what astronomers call the G-dwarf problem. The observations that there are fewer metal-poor stars in the galactic disk than simple models of chemical evolution would predict. This suggests that the thin disk formed not just through the gradual accumulation of enriched gas, but also through the infall of relatively metal-rich material from outside the galactic disk. This process, sometimes called the late heavy bombardment of galactic chemical evolution, helped ensure that even the earliest thin disk stars had metallicity sufficient for rocky planet formation. The stellar population that emerged during this epoch includes many of the stars we see in our local galactic neighborhood today. These are the stars that populate the constellations visible from Earth, the nearby stellar systems that space missions might one day visit, and the potential hosts for exoplanetary systems that might harbor life. They represent the culmination of billions of years of galactic chemical evolution, stellar systems formed from gas enriched by countless previous generations of stellar alchemy. By the end of this epoch, roughly 3 billion years ago, the Milky Way had achieved the mature structure and chemical composition that characterizes it today. The thin disk was fully established, populated with metal-rich stars capable of hosting Earth-like planets. The spiral structure had stabilized into the elegant pattern we observe, efficiently regulating star formation and chemical mixing. The galactic environment had become sufficiently stable and chemically rich to support the formation of planetary systems like our own. And the stage was now set for the final act in our galaxy's preparation for life. All the necessary ingredients were in place: a stable gravitational environment, a rich supply of heavy elements, a regulated star formation process, and vast molecular clouds ready to collapse into new stellar and planetary systems. In one particular region of the galaxy, a quiet zone about 2/3 of the way out from the center, in what would later be called the Orion Arm, conditions were particularly favorable for the formation of a planetary system that would eventually harbor life. As we reflect on this long epoch of galactic maturation, we might contemplate the extraordinary patience that the universe has shown in preparing for our existence. For billions of years before our sun was even a possibility, the galaxy was slowly but persistently creating the conditions necessary for life. Countless generations of stars lived and died to enrich the galactic medium with heavy elements. Vast stellar nurseries formed and dispersed, gradually establishing the stable spiral structure that would provide a safe haven for planetary systems. This cosmic preparation was not directed toward any specific goal. There was no consciousness guiding the process, no intention to create the conditions for life. Yet through the simple operation of physical laws, across vast scales of time and space, the universe gradually organized itself into structures of incredible complexity and beauty. In this patient cosmic preparation, we perhaps glimpse something profound about the nature of emergence, how complexity and consciousness can arise naturally from the interaction of simple rules operating across sufficient time and space. What does it mean to be the temporary beneficiaries of this vast cosmic preparation? How should we understand our responsibilities to this process that has been billions of years in the making? These questions invite not quick answers, but patient contemplation, the same kind of deep reflection that the universe itself has embodied in its long journey toward complexity and life. As our journey through galactic time approaches the era of our own solar system's formation, we find the Milky Way transformed from the chaotic collection of proto-galaxies we encountered at the beginning of our story into a mature spiral galaxy capable of nurturing life. The Great Recycling Program has enriched the galactic medium with heavy elements. The disk structure has stabilized into its current configuration, and star formation has settled into the sustainable pattern that continues today. We now enter the final chapter of our galactic odyssey, the era of the living galaxy, a time when the Milky Way not only achieved its modern structure, but also became a cosmic environment capable of supporting the emergence and evolution of life itself. This is the epoch in which our own solar system formed, in which life arose on Earth, and in which consciousness finally emerged to contemplate the magnificent cosmic story of which it is both product and witness. In the final chapter of our journey through galactic time, we arrive at the present day, an era in which the Milky Way has achieved not just structural maturity, but has become what we might call a living galaxy, a cosmic environment capable of supporting the emergence and evolution of life across countless worlds. This is the galaxy we inhabit today, a vast spiral system of over 400 billion stars, many of which may host planetary systems capable of harboring life in all its potential diversity and wonder. The modern Milky Way represents the culmination of 13 billion years of cosmic evolution. It is a galaxy that has learned to balance the competing forces that shape its development: gravity and rotation, star formation and gas consumption, chemical enrichment, and stellar feedback. The result is a remarkably stable and hospitable cosmic environment, one that has maintained essentially the same structure and star formation rate for the past several billion years, while continuing to evolve in subtle but important ways. Today's galaxy is organized into several distinct structural components, each telling part of the story we have traced through cosmic time. The ancient stellar halo, containing the oldest stars in the galaxy, preserves the memory of the violent merger epoch that gave birth to our cosmic home. These metal-poor refugees from the galaxy's youth continue their eccentric orbits through the galactic suburbs, living fossils of an era when the Milky Way was still assembling itself from smaller building blocks. The central bulge, that dense concentration of stars surrounding the galaxy's supermassive black hole, represents the gravitational heart of our cosmic home. Here, in a region smaller than the distance between Earth and the nearest star, are packed some 20 billion stars, their light collectively outshining entire galaxies. The supermassive black hole at the very center, with a mass 4 million times that of our Sun, continues to influence galactic evolution through its gravitational field and occasional feeding episodes, though it has settled into a relatively quiet phase compared to the active galactic nuclei we observe in more distant galaxies. The thick disk, product of the galaxy's architectural phase, forms an intermediate layer between the ancient halo and the more recent thin disk. Its stars, now middle-aged by stellar standards, represent the generation that witnessed the galaxy's transformation from a chaotic collection of stellar systems into an organized spiral structure. They carry in their chemical compositions the signature of the galaxy's early chemical enrichment, showing metallicities intermediate between the metal-poor halo stars and the metal-rich stars of the thin disk. But it is the thin disk, our immediate cosmic neighborhood, that most directly shapes our experience of the galaxy today. This remarkably flat structure, containing about 2/3 of all the stars in the Milky Way, is where most of the galaxy's ongoing star formation takes place. It is home to the brilliant spiral arms that give our galaxy its characteristic appearance, vast stellar nurseries, where new generations of stars continue to be born from the enriched gas that has been accumulating for billions of years. The spiral structure of the modern galaxy is a dynamic, ever-changing feature that represents one of the most beautiful examples of self-organization in nature. The spiral arms are not permanent structures made of the same stars, but rather density waves that propagate through the galactic disk like ripples on a pond. As the galaxy rotates, different stars pass through these spiral arms at different times, experiencing enhanced star formation when they encounter the compressed gas within the arms, before emerging into the quieter regions between them. Our own solar system currently resides in a minor spiral arm called the Orion Arm or Local Spur, located about halfway between two major spiral arms. This location has proven advantageous for the development of life on Earth, as it has protected our planet from the intense radiation and frequent supernova explosions that characterize the more active stellar nurseries within the major spiral arms. Our position in this cosmic suburb has provided billions of years of relative stability, allowing life to evolve and flourish without frequent disruptions from galactic catastrophes. The star formation process in today's galaxy continues the pattern established during the thin disk formation epoch, but with some important differences. The overall star formation rate has declined from the peak levels of earlier epochs, as the galaxy has consumed much of its readily available gas supply. However, star formation continues at a steady pace, creating about 1 to 2 new stars per year from the remaining reserves of molecular gas scattered throughout the disk. Modern stellar nurseries, like the nearby Orion Nebula, provide us with spectacular glimpses into the ongoing process of star and planet formation. These regions, where hot young stars illuminate vast clouds of gas and dust, are the contemporary equivalents of the stellar nurseries that gave birth to our own sun 4.6 billion years ago. Observations of these star-forming regions reveal that planet formation appears to be a common outcome of the stellar birth process, with protoplanetary disks observed around the majority of newly formed stars. The chemical composition of gas in today's galaxy reflects billions of years of stellar recycling and chemical enrichment. The abundance of heavy elements has increased by more than a factor of 10 since the galaxy's formation, reaching levels that make possible the formation of rocky planets, complex atmospheric chemistry, and the organic molecules that serve as the building blocks of life. This chemical richness is not uniformly distributed throughout the galaxy. There is a metallicity gradient, with the highest concentrations of heavy elements found in the inner regions of the disk, where star formation has been most intense throughout galactic history. One of the most remarkable aspects of the modern galaxy is the diversity of planetary systems it contains. Recent discoveries of exoplanets, planets orbiting other stars, have revealed that planetary systems are common throughout the galaxy, with estimates suggesting that most stars host at least one planet. These planetary systems show an incredible diversity of architectures, from hot Jupiters orbiting close to their parent stars to systems with multiple Earth-sized planets in their habitable zones. The concept of the galactic habitable zone, the region of the galaxy most conducive to the development of life, has become increasingly important in our understanding of the modern Milky Way. This zone, roughly coincident with the region where our solar system formed, represents the optimal balance between chemical enrichment and environmental stability. It is far enough from the galactic center to avoid frequent disruptions from supernovae and gamma-ray bursts, yet close enough to benefit from the chemical enrichment provided by earlier generations of stars. Within this galactic habitable zone, astronomers have identified numerous stellar systems that might host Earth-like planets capable of supporting life. The Kepler Space Telescope and other planet-hunting missions have discovered thousands of exoplanets, including many that orbit within their star's habitable zone. The the region where liquid water could exist on a planet's surface. While we have not yet detected definitive signs of life beyond Earth, the abundance and diversity of potentially habitable worlds suggests that our galaxy may be teeming with life in forms both familiar and unimaginable. The modern galaxy is also characterized by its ongoing interactions with smaller satellite galaxies. The large and small Magellanic Clouds, visible as fuzzy patches in the southern sky, are gradually being disrupted by the Milky Way's gravitational field. Gas stripped from these satellite galaxies is currently falling into our galaxy, providing fresh fuel for future generations of star formation and slightly altering the galaxy's structure in the process. Looking ahead, astronomers can predict the future evolution of our galaxy with considerable confidence. The most dramatic change will occur in about 4 billion years, when the Milky Way is expected to collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor. This collision will be a gentle gravitational dance, rather than a violent crash, as the vast distances between stars mean that actual stellar collisions will be extremely rare. The merged system, sometimes playfully called Milkomeda, will be larger and more elliptical than either of the current galaxies, representing a return to the merger-driven evolution that characterized the early universe. But even this future collision should not disrupt the fundamental habitability of our galaxy. The enlarged merger remnant will continue to host star formation, chemical enrichment, and planetary system formation for trillions of years into the future. Life, if it has indeed emerged elsewhere in our galaxy, will have ample time and opportunity to adapt, evolve, and spread throughout this expanded cosmic environment. The galaxy we inhabit today is thus both an endpoint and a beginning, the culmination of 13 billion years of cosmic evolution and the foundation for countless future chapters in the ongoing story of life and consciousness in the universe. We find ourselves privileged to live during an era when the galaxy has achieved optimal conditions for the emergence and evolution of life, when the chemical enrichment of previous epochs has created the material foundation for complex chemistry and biology, and when the structural stability of the galactic disk provides a safe harbor for the long-term evolution of planetary systems. Perhaps most remarkably, we live in an era when conscious beings have emerged to contemplate this vast cosmic story. For the first time in the galaxy's history, the universe has become aware of itself through the emergence of consciousness on at least one small planet orbiting an ordinary star in an unremarkable spiral arm. We are the galaxy's way of knowing itself, temporary arrangements of atoms that have achieved the remarkable ability to trace their own cosmic origins back through billions of years of stellar evolution and galactic development. This perspective transforms our understanding of our place in the cosmos. We are not separate observers of the galaxy's evolution. We are active participants in its ongoing story. Our emergence represents a new chapter in cosmic evolution, one in which matter has achieved the ability to contemplate its own origins and to consciously participate in shaping its own future. Through science, art, exploration, and the countless other expressions of human creativity and curiosity, we extend the galaxy's capacity for self-awareness and self-transformation. The living galaxy of today thus encompasses not just the 400 billion stars and their planetary systems, but also the consciousness that has emerged to study and appreciate this vast cosmic home. In our telescopes and spacecraft, our theories and equations, our poetry and music inspired by the night sky, the galaxy has developed new organs of perception and expression. We are, quite literally, the galaxy becoming aware of its own magnificent story. Contemplative moment, our conscious participation. As we near the end of our journey through galactic time, we might pause to contemplate the extraordinary fact of our own existence as conscious observers of this cosmic story. Of all the chapters in the galaxy's 13 billion-year history, we happen to live during the brief epoch when consciousness has emerged to reflect upon the vast processes that gave birth to stars, planets, and life itself. This is not merely a fortunate coincidence, but a profound responsibility. We are the galaxy's memory, the living repositories of its ancient history. In our bones, we carry iron forged in stellar cores billions of years ago. In our DNA, we preserve the chemical innovations of countless generations of life. In our minds, we hold the accumulated wisdom of centuries of human observation and reflection on our cosmic home. What does it mean to be conscious participants in the galaxy's ongoing evolution? How might our awareness and understanding of this vast cosmic story shape our choices and actions? These questions remind us that we are not merely passengers on a cosmic journey, but active agents in its continuing unfoldment. In recognizing our deep connection to the galaxy's history, we perhaps find both humility at our cosmic insignificance and wonder at our unprecedented role as the universe's way of knowing itself. As our gentle journey through 13 billion years of galactic time draws to its close, we find ourselves not at an ending, but at a new beginning. The story we have traced together, from the violent merger of proto-galaxies through the patient construction of spiral architecture, from the great recycling program that enriched the cosmos with heavy elements to the emergence of the thin disk where our own solar system would eventually form. This story continues to unfold around us with each passing moment. The Milky Way we inhabit today is both the culmination of this vast cosmic epic and the foundation for countless future chapters yet to be written. In the stellar nurseries scattered throughout the spiral arms, new generations of stars continue to be born from gas, enriched by billions of years of stellar alchemy. Around these young stars, protoplanetary disks are condensing into rocky worlds that may one day harbor their own evolutionary stories. And somewhere among the 400 billion stars that populate our galactic home, other forms of consciousness may already be awakening to contemplate their own cosmic origins. Our journey has revealed the Milky Way to be far more than a collection of stars scattered through space. It is a vast, interconnected system in which every component plays a role in the ongoing evolution of the whole. The ancient halo stars, products of the galaxy's violent youth, continue to influence galactic dynamics through their gravitational effects. The thick disk stars, witnesses to the galaxy's architectural phase, preserve in their chemical compositions the memory of early chemical enrichment. The young, metal-rich stars of the thin disk represent the current generation of the galaxy's stellar population, formed from material that has been recycled countless times through the cosmic furnaces of previous stellar generations. This perspective transforms our understanding of our own place in the cosmic order. We are not isolated beings living on a lonely planet in the vast darkness of space. We are integral participants in the galaxy's ongoing evolution, temporary organizations of matter that have achieved the remarkable ability to reflect upon the cosmic processes that gave birth to us. Every atom in our bodies carries the signature of this vast galactic story, the hydrogen forged in the Big Bang's first moments, the carbon created in stellar cores, the oxygen dispersed by dying stars, the iron scattered by supernovae explosions. The story we have explored together also reveals the profound interconnectedness of all cosmic processes. The formation of our solar system was not an isolated event, but the culmination of billions of years of galactic evolution that created the necessary conditions for rocky planet formation and the emergence of life. The chemical elements that make life possible were forged in stellar cores over countless generations of stellar evolution. The stable galactic environment that has allowed life to flourish on Earth for billions of years is the product of the galaxy's long journey towards structural maturity. As we contemplate this vast temporal tapestry, we might reflect on the patience that characterizes all cosmic processes. The galaxy did not rush toward its current configuration, but achieved it through the gradual accumulation of countless small changes over billions of years. Stars formed, evolved, and died according to the patient mathematics of nuclear physics and stellar structure. Heavy elements accumulated slowly in the galactic medium through the gentle process of stellar recycling. The spiral structure emerged and stabilized through the subtle interplay of gravitational dynamics and gas flow patterns. This cosmic patience offers a profound lesson for our own lives and societies. The most significant transformations often occurred not through dramatic, sudden changes, but through the accumulation of countless small steps taken consistently over long periods of time. Just as the galaxy achieved its current complexity through billions of years of patient evolution, perhaps we too can achieve meaningful transformation through sustained effort applied with the same kind of cosmic patience. Our exploration of galactic time also illuminates the remarkable fact that we live during a special epoch in cosmic history. The universe is currently in what astronomers call the stelliferous era, the age of stars, when conditions are optimal for stellar formation, planetary system development, and the emergence of life. This era began when the first stars ignited in the cosmic dawn and will continue for trillions of years into the future. But we happen to live during the relatively brief period when the galaxy has achieved the perfect balance of chemical enrichment and structural stability necessary for complex life. In earlier epochs, the galaxy was too young and metal poor to support the formation of Earth-like planets. In the distant future, as star formation gradually declines and the galaxy's gas supply is exhausted, conditions may become less favorable for the emergence of new life. We find ourselves living during the galaxy's prime time for biological evolution, when billions of years of cosmic preparation have created conditions that are as close to optimal for life as the universe may ever achieve. This realization brings with it a sense of both privilege and responsibility. We are the beneficiaries of the longest and most complex preparation in cosmic history, 13 billion years of stellar evolution, chemical enrichment, and galactic development that have created the conditions for our existence. This vast cosmic investment in the creation of life-supporting environments suggests that consciousness and intelligence may be among the universe's most precious and significant achievements. The story of our galactic home also reveals the profound unity underlying the apparent diversity of cosmic phenomena. The same physical laws that govern the behavior of subatomic particles also shape the evolution of galaxies across billions of years. The nuclear fusion processes that power stellar cores operate according to the same quantum mechanical principles that govern chemical bonding in living cells. The gravitational forces that organize galactic structure also determine the orbital mechanics of planetary systems and the circulation patterns in planetary atmospheres. This underlying unity suggests that consciousness and life are not accidental byproducts of cosmic evolution, but natural expressions of the universe's fundamental tendency toward increasing complexity and organization. Just as gravity naturally organizes matter into stars and galaxies, and stellar nucleosynthesis naturally creates the chemical elements necessary for rocky planets, perhaps the emergence of life and consciousness represents the natural continuation of this cosmic trend toward greater complexity and self-organization. As we reach the end of our journey through galactic time, we stand at a unique moment in cosmic history. Behind us stretches the vast epic of galactic evolution that has brought our cosmic home to its current state of complexity and beauty. Before us lies the even vaster future of galactic evolution, with trillions of years during which new stars will form, new planets will condense, and new possibilities for life and consciousness will emerge. We are the bridge between past and future, the living link connecting the galaxy's ancient history with its unlimited potential. In our genes, we carry the chemical innovations of 4 billion years of biological evolution on Earth. In our minds, we preserve the accumulated knowledge of centuries of human scientific investigation. And in our actions and choices, we shape not only our own future, but contribute to the ongoing evolution of consciousness in the cosmos. The galaxy that cradles us is both unimaginably vast and intimately personal. It spans over 100,000 light years from edge to edge, contains hundreds of billions of stars, and has been evolving for most of the history of the universe itself. Yet it is also our most immediate cosmic environment, the stellar system, that provides the gravitational, chemical, and energetic context within which all of terrestrial life exists and evolves. Perhaps the most profound lesson of our galactic odyssey is the recognition that we are not separate from the cosmic processes we have explored, but are their most recent and remarkable expression. The carbon in our cells was forged in stellar cores. The oxygen we breathe was created by massive stars and dispersed by supernovae, and the calcium in our bones was scattered through space by stellar winds billions of years ago. We are walking, thinking repositories of the galaxy's long history of chemical evolution. This perspective offers a new foundation for understanding our relationship with the natural world and with each other. If we are all made of recycled star stuff, if we all share the same cosmic heritage stretching back to the galaxy's formation, then perhaps we can find in this shared origin a basis for deeper connection and mutual understanding. The atoms in our bodies have been cycling through the galaxy for billions of years, temporarily organized into countless different forms before coming together in the specific arrangements that constitute our individual existence. The galaxy's story also suggests that patience and persistence are among the most fundamental virtues in the cosmos. The transformation of simple hydrogen and helium into the complex chemistry of life required billions of years of stellar recycling. The organization of chaotic proto-galaxies into elegant spiral structure demanded eons of gravitational sculpting. The emergence of consciousness from simple chemical processes involved billions of years of biological evolution. Perhaps we can learn from this cosmic example to approach our own challenges with similar patience and persistence. As we prepare to transition from this galactic perspective to the more intimate story of our own solar system, we carry with us the profound realization that Earth is not an isolated oasis of life in a hostile universe, but rather the natural and perhaps inevitable result of billions of years of cosmic evolution. Our planet, our solar system, and we ourselves are all expressions of the galaxy's long journey toward complexity and consciousness. The Milky Way has provided the stable, chemically rich environment necessary for the formation of our solar system and the evolution of life on Earth. Its spiral structure has regulated star formation and chemical mixing. Its recycling program has created the heavy elements that make rocky planets possible. Its gravitational architecture has provided the long-term stability necessary for evolutionary processes to unfold over geological time scales. Now, having traced the galaxy's 13 billion-year journey from its birth in the cosmic dawn to its current state as a mature, life-supporting stellar system, we are ready to focus our attention on one particular stellar nursery where, 4.6 billion years ago, a cloud of gas and dust, enriched by all of this galactic evolution, began to show the first signs of gravitational collapse that would eventually give birth to our Sun, our Earth, and ultimately to us. Within one of the Milky Way's spiral arms, in a quiet region some 26,000 light-years from the galactic center, a cloud of gas and dust enriched by billions of years of stellar evolution began to show signs of gravitational collapse. This seemingly unremarkable event, occurring in an ordinary part of our galaxy during what appeared to be a typical epoch of galactic evolution, would ultimately lead to the formation of a planetary system capable of supporting the emergence of life, consciousness, and the very capacity for cosmic contemplation that has allowed us to trace our origins back through the vast expanses of galactic time and space. The story continues, as it always has and always will, with the same patient unfolding of cosmic potential that has characterized every chapter of our galactic journey. In the gentle collapse of that ancient molecular cloud, all of the galaxy's billions of years of preparation would finally bear fruit in the form of a small, rocky planet orbiting an ordinary yellow star, a world that would become the stage for the next great chapter in the ongoing story of cosmic evolution and the emergence of consciousness in the universe. If you found this gentle journey through our galactic home helpful for contemplation or rest, consider staying with us as we continue to explore the magnificent story of cosmic evolution.